problems with these lines in Chapter 1.3.2 of Algebra 1B. Remember, last video we discussed how to start setting these up and how to start identifying variables. In this video, we're going to see how we can use slopes and units as clues and set up and represent problems with equations, graphs, and tables. At the very end of the last video, I showed how these tend to take two forms. One is slope-intercept form, y equals mx plus b. You'll use that whenever you have an independent variable or if you have a rate. If you have a rate of some sort, you're going to have a slope. Okay, slopes give you rates, and that's why you have a slope-intercept form. Standard form happens if you are combining two things together, like cows and ducks, or dogs or cookies or something. And it's in ax plus by equals c for standard form. One thing to note that maybe you've thought about, maybe you haven't. These two b's are different, right? This b is the y-intercept. That's why it's lowercase. This b is just a coefficient on one of the variables. That's why it's capitalized. So different b's for those two forms. Okay, let's discuss some scenarios with rates. We're going to talk about rates for a second. Some types of seaweed can grow at a rate of 11 inches per day. I looked that up online. This is in ideal conditions and not for a long period of time, I don't think. Currently, a seaweed plant is 4 feet long. Now remember, there isn't like a problem in here anywhere. This scenario has no question of any sort. It's not saying how long until the seaweed is 20 feet long, anything like that. It's just giving you information, and we want to start to make sense of it, find places to put the information. One thing that I would caution you to notice very quickly, this rate came to us in inches, 11 inches per day. We would write that as 11 inches per 1 day, or just per day. However, this right here was in feet. If you have things that are in two different units, inches and feet, convert them into the same unit. Since our rate is dealing with inches, our rate has inches, I'm going to take this and turn it into inches also. 4 feet is actually 48 inches. Let's do 4 times 12. So I'm not going to deal with 4 feet, I'm going to deal with 48 inches. Okay, now it says identify the independent and dependent variables. Here's what's so nice about slopes, okay? I'm going to take the slope, the rate, which is 11 inches over 1 day. And I know that slopes are the y divided by the x. So I'm just going to state that my y variable is inches and my x variable is days. It's that simple. The thing on the bottom of your slope is your x variable, because slope is rise over run, or change in y over change in x. So the thing on the bottom is x, the thing on the top is y. This means that my independent variable is days, or time, and my dependent variable is inches, or distance. We know we have an independent or dependent variable because we have a slope, we have a rate. If you have a rate, that means something depends on something else. In this case, the growth depends on how much time has passed. So time is independent, growth is dependent because growth depends on something. Okay, so we have a slope, 11 inches per day. That's our rate. Since we have a slope, setting up an equation is pretty straightforward. We're going to do y equals mx plus b, but we know the slope is actually just 11. 11 over 1 is just 11. And this right here is our y-intercept. The y-intercept is always your starting point. It's going to be y equals 11x plus 48, and this is the equation that models that scenario. In 1 day, it'd be 59 inches. In 2 days, it'd be 70 inches. In 3 days, it'd be 81 inches. We could even maybe say a day ago it was 37 inches if it has been growing this way for a while. Okay, take a second and see if you can identify the variables in number 2, which is independent, which is dependent. Hopefully you actually paused and tried. Please do that. This right here is our slope. That's our rate. Rate and slope are going to be the same thing. So 3 miles per 1 hour Well, the top variable is going to be miles. Y is going to be miles. X is going to be hours. Those are my variables. X represents the hours we've been running. Y represents the miles we have run. So my independent variable, which is X, is hours. My dependent variable, which is Y, is miles. Pretty straightforward. Set up an equation that models a scenario. Well, I know the equation is going to be in the form y equals mx plus b, and I already know what m is. M is just the number 3, right? This is our slope, 3. The question is, where's our starting point? We've already run 2 miles, so it's 3x plus 2. In 1 hour from now, so like starting at 2 miles, in 1 hour we'd go 5 miles, in 2 hours we'd be at 8 miles, and in 3 hours we'd be at 11. This equation models how much distance we have covered given a period of time, starting from 2 miles. Okay, we'll do one more, and this one will actually graph. It says every possession you score 3 points. Now that possession, I'm thinking sports, could be basketball, could be football. Sorry, it says every 4 possessions you score 3 points. Whatever the sport is, doesn't really matter. Every 4th time that you have the ball, there's some possession for you, you're scoring 3 points. Well, this is the first slope we've had that has a number besides 1 in the denominator. Okay, our slope, or our rate, is going to be this. Every 4 possessions, you score 3 points. Think of that as 3 points per 4 possessions, and the word per means divide. 3 points per 4 possessions, we divide 3 per 4, 3 divided by 4. Possessions is just kind of how we're measuring time. Instead of time being in minutes, time is how often we have the ball. So a possession is really still a measurement for time. It's still going to be our independent variable. The dependent variable, which we know is y, well, the number of points we have depends on the number of possessions we have. If we have the ball for 10 possessions, we'd expect to have scored 6 points. But 12 possessions, we score 9 points. So this is the first time we've had a number down here in the denominator that doesn't really change anything except for it makes things kind of nerve-wracking because we have a fraction. But here's our equation. See if you can set up the equation. Pause the video and try to set it up. It's actually just y equals 3 over 4x. We weren't told if we've already scored any points. So we can't say like we're starting at 10 or starting at 2 or something. We're just going to assume we're going from 0 and y equals 3 over 4x. Okay, we're asked to graph the scenario and give a table. I think usually giving a table first really helps you with the graph. Here's how this actually works. Like once you start talking about sports, you could say 1 and 0.75. And what that means is since x is possessions, on the first possession you score 0.75 points. And on the second possession you score 1.5 points. And we know that in reality you can't score 0.75 points in most games, but it's easier to think about things on a per possession basis so that you can identify how you're doing in general, not in terms of whole numbers, but in terms of decimals that you can compare. So if you ever are following stats for sports like basketball, baseball, football, any team sport, probably even like tennis, golf, the stats that come, they don't come as whole numbers, even though only whole numbers tend to make sense. Because they just can't, and that's okay, we just live with that. It's like, you know how we say that in the US, every family has 2.2 kids? And I think that number is dropping. That was a stat like 12 years ago. Well, obviously, nobody has 0.2 of a kid, unless we're like extremely horrible people that think you can have less than a whole person somehow. What that means is more families have 2 kids than 3. Most families have 2 kids. Some kids have 3. We would think like 8 families have 2 kids, and 2 families have 3. So even though we can't have 2.2 kids per family, we can talk about it like 2.2 is reasonable. In the same way, we can't score 0.75 points, But we could think of this as every possession we're scoring 3/4 of a point. But to actually graph this, what I want to do is think about easy ones. So, if there's been no possessions, I've scored no points. I'm not crazy, I don't write a 4. If there have been 4 possessions, I score 3 points. Because every 4 possessions, I score 3 points. So 8 possessions, 6 points, 12 possessions, 9 points. This actually clues us into a really nice way to go about finding points and graphing. The denominator here was 4. The denominator of my slope is 4. So I only plug in numbers that are multiples of 4. It makes graphing and finding points really, really simple if you count by the denominator of your slope. So now I'm going to graph the points. Let me just make a nice little, I'll use white here. Here's my y-axis. Here's my x-axis. I'm not going to have negative points, so I'm not going to have negative x or y values, so I'm just graphing in quadrant 1. Did you notice how on the x-axis I counted by 4s, because that's what I did here. On the y-axis I counted by 3s, because that's what I did here. Let's not make this tough, right? Like, make the graph readable, but also simple. I'm going to make it as graphable as I can. I have the point 0, 0, I have the point 4, 3, I have the point 8, 6, and have the point 12, 9. The graph would look like this. I'm going to label the x-axis is possessions. The y-axis is points. I'm going to put a y here and an x here. And at this point, I don't really need to do a checkpoint because that's what this was. My table and my graph are matching. There's my checkpoint. I guess I should check to make sure it matches the equation. So I'm going to grab the point 8, 6. Here's a point 4, 3. I'm going to plug in 8, 6. I'm going to check the point 8, 6. So I have y equals 3 over 4x. I'm going to plug in a 6 for y. I'm not going to write so diagonal anymore. 3/4 times 8 is something we need to be able to handle. Make that a fraction, 8 over 1. 8 divided by 4 becomes 2 over 1. So I'm multiplying across the top. And 6 equals 6. Boom, checks. Okay, let's do some problems that don't have rates. These are going to set up in standard form, where we have codependent variables. There are a total of 30 animal feet in a barn full of cows and ducks. Now you might read this and be like, what do I do with that? Like, okay, interesting information, but we can kind of ask the question. Like, that sort of begs the question, how many cows are in there and how many ducks are in there? And are all things possible? Could there be 7 cows and this still work out? My variables, the things that I don't know but I can find, is x will represent number of cows, and y will represent number of ducks. Those are things that I don't know, but I could find. This is a codependent scenario, because if there's more cows, there's fewer ducks, but if there's more ducks, there's fewer cows. Okay, the equation here is odd at first. Hopefully this gets more natural for us. What's different about cows and ducks, obviously? Cows have 4 feet, ducks have 2. So I'm going to write 4x plus 2y, and that has to come out to 30, because that's how many feet there are. This right here is 4 feet per cow. 4 feet per cow. This is 2 feet per duck, and altogether there's 30 feet. This is a foot equation. Feet plus feet equals feet. Okay? 4 feet per cow, 2 feet per duck, total of 30 feet. It could be that there are, 6 cows and 2 ducks. No, 3 ducks. That's a possibility. It could also be that there's just 15 ducks and no cows. We know that there has to be some ducks, though. We can't have this all cows because 30 can't divide by 4. So there'd have to be at most 7 cows with 1 duck. Okay, pretend this is the word plan and not plant. You plan to use all your money at lunch. You have $20, fries cost $1, and burgers cost $3. Well, again, there's no independent or dependent thing here. We could buy a bunch of fries, we could buy a bunch of burgers, but we can't just state that exclusively one of them controls the other. This is a codependent scenario. X is just going to stand for number of burgers. I'll do number of fries. Fries was listed first, so I'm going to put fries first. And Y equals number of burgers. But one doesn't depend on the other. It's a codependent scenario. Now, the equation here, excuse me, the equation here is going to be kind of similar to what happened last time, where the coefficients matter. The coefficient means the number that multiplies your variable. If burgers cost $3, then it's $3 per burger, 3y. If fries cost $1, then it's $1 per fry. $1 per fry plus $3 per burger, and we have to come out to $20. 1x plus 3y equals 20. I would like to make this just a little bit prettier. Oh well, I'm not gonna. Here's our equation. 1x plus 3y equals 20. Now, there's a bunch of possibilities, right? Like, I could buy no burgers and 20 fries. That would cost $20. I could buy at most 6 burgers and 2 fries. That would cost $20. I could also buy like, let's just say 5 burgers and 5 fries. Sounds like a pretty great meal. These ones all seem pretty great. This one sounds really awful. These are all possibilities. So let me graph these points. Fitting 20, 0 onto here is going to be a bit tough. So I'm going to count by 2s, I think. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I counted by 2s on the x-axis because the x-axis is going to go as high as 20. On the y-axis, I think I'll just count by 1s because the y-axis only goes as high as 6. I kind of missed. My first point is actually at 2. My first point of 2 was actually put at 1, so I'm going to slide these up 1. Now notice how I just really quickly made a table, and the table told me which points were possible. And then from there I could count out the scales on my graph. I'm not going to actually find the x or y-intercept right now because I can just plot points. I have the point 20, 0, which is here. I have the point 5, 5, which is about here-ish. I have the point 2, 0. No, that's not correct. It's 2, 6. Let's find one more. What if I bought 2 burgers? If I bought 2 burgers, that's $6, so I could buy 14 of these. That'd be here. This is the point 14, 2. This is the point 2, 6. Let's connect these dots. You might be thinking, wait, do you actually want to connect the dots? Don't we know that not everything is possible? Like, we can't actually buy a half of a fry or a quarter of a burger. Yeah, but at this point, we just connect the dots because that shows how the trends are happening. If you didn't connect the dots, that'd be fine. But there's my graph. Okay, I'm going to label this. I've got a few points put down. I'm going to label my x and y axis. I know that x stands for number of fries. I know that y stands for number of burgers. And it's interesting that as I buy more fries, I have to buy fewer burgers. As the graph goes to the right, it goes down, because if you buy more fries, you buy fewer burgers. That kind of makes sense. To recap, units and rates are a great way to identify variables and figure out if the scenario is independent or dependent, or instead it's codependent. If you can see you have a rate, you'll probably be using slope-intercept form, which is really nice. Tables of data make it easier to make graphs and equations. Next video, we're going to start solving equations by graphing. All that means is graph two lines at the same time and see where they cross. See you then.
There's a lot of pressure to make these little outro videos. I'm supposed to tell you to do all these things like subscribe to me, love me, I don't know, whatever. Here's an ellipse, and if I pull the two foci really close to each other, you get what looks like a circle. If I pull them farther apart, it'll eventually break through and form a hyperbola. I'm not sure why those little red lines there are being traced around, but whatever they are. Just so you know, if you'd like to have curriculum and worksheets to go with these videos, check the links in the description down below. And that's all I got.